All right, just a few more things that I want to go over here, and we'll finish up this topic really quickly. Remember I gave you some of the formulas as just showing you math relationships? Well, on your reference table, there's another formula called the rate of change. And the rate of change, very simply, is the change in field divided by the time it took for that change to take place. So, what is field? A field is anything that's being measured or studied at the time. That's very generic, I understand that. A field could be gravity. A field could be atmospheric pressure. A field could be magnetic fields. A field could be temperature. A field could be, what else did I say? Wind speeds. So anything that could be measured and studied, that's the field. Divided by the time it took the field to change. So if I'm looking at my thermometer on my desk and it reads 20 degrees Celsius and I turn my lamp on and I notice after 5 minutes it reads 25 degrees Celsius, well, to figure out the rate of change, I'd have to look at the difference. That's what this delta means. That's what this triangle means, a change between the two temperatures. And I divide that by the time it took for the change to take place. So if I had 20 degrees when I started and I had 25 degrees at the end of my time frame, it would be 25 degrees minus 20 divided by how much time it took for me to go with the study. How long did it take the time for the study? So if it was 5 minutes, then it would be 25 minus 20, which is 5, divided by 5 minutes. So it would be 1 degree per 1 minute, or 1 degree per minute would be my rate of change. For every minute that went by, I changed my temperature by 1 degree. So it's important you write the units down, and it's important that you set up the formula correctly. So be careful with that. It's on your reference table. And we're going to work on this. We're working with this throughout our labs and in problems in class. Another example. And again, if I'm blocking you with my picture, then you'll have all this in your notes as well. I'll change this. I'll move this. Okay. Okay. A cyclical change is something that repeats itself. Something that follows a cycle is repeating or it repeats its performance. It repeats its function. That's a cyclical change. Sun rises, sun sets, sun rises again, it sets. That's cyclical. So sunrise and sunset is cyclical. Moonrise, moonset, cyclical. The yearly pattern change of the constellations, that's cyclical. We call them seasons, seasonal changing constellations, but it's still cyclical. Anything that shows a pattern change is a cyclical change. The phases of the moon, that pattern repeats itself. That's a cyclical change. Here's some examples. Interface. An interface is a boundary. An interface is a boundary where two maybe different densities are taking place, two different energies are being transmitted, and there's always a disturbance at an interface. There's always a disturbance at an interface. When you have a cold front of air hitting a warm front of air, there's an interface where the two intersect each other, where they collide. That's an interface. You usually get storms. Go outside and look at stars, especially now in the summertime, fall time. You look up at the sky and you look at stars and you notice that they twinkle. That twinkling is because there's an interface between space and the atmosphere, and the disturbance makes like waves at the surface of the atmosphere, and that waving causes the light from the stars to bend. We see the bend as a twinkle. Sometimes it's brighter, sometimes it's dimmer, sometimes it's brighter, sometimes it's dimmer. That's a twinkle, and somebody made a song about it. Okay, those are just some examples. We're going to look at them as the year unfolds. We're going to see more and more different interfaces as we move along. But an interface is basically a boundary between two structures. Very simple. I mean, there's a simple example. A condition that exists a lot in earth science is called dynamic equilibrium. A condition that exists a lot is called dynamic equilibrium. And basically all it means is that as a change is occurring, it's occurring at the same pace as something else. For example, give you an example. If I give you a cup of water and I fill the cup of water up to the top, and then I poke a hole in the bottom of the cup, on the side, but on the bottom of the cup, you're going to watch the water drip out, leak out. And as the water leaks out, what happens to the water level inside the cup? The water level drops. Now if I take that same cup, hold my finger over the hole, and I fill the water back up to the top, but now I put it underneath a water faucet and turn on the water faucet, and the water going into my cup has the same speed as the water coming out of my cup when I take my finger away. What happens to the level of the water in the cup now? So the amount of water going in equals the amount of water going out. What happens to the level of water inside my cup? It remains constant. So we say that the object has reached a dynamic equilibrium. There are changes going on. I have new water going in. I have old water coming out. But the overall condition has remained constant. That's dynamic equilibrium. Here's an example in earth science. Every single day, there is magma, molten rock material, coming up from the depths of the earth and spreading out along the earth's surface, creating more earth's surface. Yet the size of the earth remains constant. Why? Because the rate at which the earth's surface is being created is also equal to the rate at which the earth's surface is being destroyed in other areas. In some areas, earth's surface is being thrown underneath another surface of the earth. In some areas, it's just wearing down and being transported and destroyed and moved into different areas. In any case, the rate at which the Earth's surface creates itself is equal to the rate at which the Earth's surface destroys itself, so the Earth maintains a dynamic equilibrium in its size. It doesn't change. It's just an earth science example. A funny example, don't ever do this, but a funny example is what I have here is somebody on an escalator. If you're going up an escalator, or let's say you want to go up an escalator, but the escalator you're on is going down. Okay? So the stairs are going down. If you walk on those stairs at the same speed that those stairs are going underneath you, you will maintain the same location on the escalator. You will not go up the escalator. You will not go down the escalator. In a sense, you would have achieved dynamic equilibrium. So the floor underneath you is changing. You're constantly moving your legs. That's all, you're all trying to make these changes happen, but because the conditions are happening at the same rate, you're not going anywhere. You've reached dynamic equilibrium. You want to break dynamic equilibrium, you either have to walk faster so you can go ahead of the escalator, that will make you climb the escalator, or you go slower and the escalator will bring you down to the bottom. But if you go at the same speed as the escalator, but in the opposite direction, you will maintain your location on the escalator. That's another form of dynamic equilibrium. And now there's my example. I forgot I even had it here. So there's my example of the styrofoam cup. And here it is in visual. So here you have the amount of water going into the tank is equal to the amount of water going out of the tank. So the tank's water level remains constant.